In this problem, we're going to solve for the force between two parallel wires with current acting on them. And the question is, what's the magnitude and the direction of the forces acting on wire 1 and wire 2? So wire 1, let's say, is just moving straight in the plane of this board straight up, and parallel to that is wire 2, which is there, and wire 1 has the current that flows in this direction, wire 2 has the current flowing in the opposite direction, and their distance between them, the centers of the wires, is distance d. And the question is what magnitude and direction of the force, and knowing what we learned about magnetic fields and forces and right-hand rules, solve it now. So pause the video, solve it, and then I'll review the answer. The solution to this problem involves two parts. The first is determining the magnitude of the magnetic field at the location of each of the wires. So during the first part, the magnetic field generated by a current flowing in a wire is given by this formula. The magnetic field vectorial magnitude and direction is permeability of free space, which is 4 pi times 10 to the minus 7 Tesla over meter per amp, times the current amplitude in amps divided by 2 pi over the distance from the wire. And the vectorial direction of this magnetic field is given by the right-hand rule. So we're going to start out, we're going to divide the problem into this, not only two parts, but two parts on determining the magnetic field. So first of all, we're going to say this wire, from the top view, wire 1 has current flowing up through it. So in the top view, that looks like that's the arrow. And we're going to think about what's the magnitude of the magnetic field at location where this second wire is produced by this first wire, and the current through that first wire. So just viewing this as a point in space now, so I have some point in space from the top view, which is the distance d away from this first wire. First of all, the vectorial direction you put for this right-hand rule determining how a magnetic field is generated on a wire, you put your thumb is the input in the direction of the current, which is up, which is in the top view up, and then you, with your right hand, spin around. So in this position, you can see that the magnetic field is perpendicular to this distance and going in the upward direction. So that's the direction. Well, in the top view, it's going into the board. So you can put here, you can see if I put my current there, I'm spinning. The magnetic field direction for B at a location is into the board. And from the top view, that looks like this. So it's into the board there. Top view is this. Okay, so now we know at location of the second wire, what's the magnetic field created by wire 2. Now let's do the opposite. So now wire, and this one I have the current flowing downward, which is into the board at location 2. What's the magnetic field produced at this location where this wire happens to be caused by this one? So current's flowing down, so right-hand rule, so that means also shows, put the thumb in the direction of the current, spin around, also shows that for this one, this is the magnitude of this magnetic field generated by that. It's not generated by itself, but generated by the other current. So here, top view, put your thumb in direction, rotate around, right hand. So there's my beta produced at the wire 1 location caused by the current flowing in wire 2. Okay, so now we know directionality. We know it's perpendicular to this distance between them, and here's this magnitude. In this case, it's always perpendicular to free space over 2 pi, and then it's this magnitude is proportional to the current flowing in the wire that's producing it. So in this case, the magnetic field is produced by this current. It's at those locations, but produced by this one. So it's the magnitude of I1, and then it's divided by the distance or the radius, whatever you can consider it as the distance between them. And then for this case, what's the magnetic field at this location where this wire is produced by this wire, it's again permeability of free space over 2 pi. This time this is the current that produces it, which is I2 is producing this magnetic field, so it's I2, and again it's D is the distance between them. So that's the magnitude and the directional vector of this magnetic field at these two different locations. So at this location produced by this one, and then at this location produced by this one. And you can see the magnitudes are different because they're different by depending on what the relative magnitudes of the currents flowing. I didn't say the currents are the same value, I just said those are the current flows. And so now we know at a location what the directionality of the magnetic field is, and I know a current level, so we can use our other equation to determine what's the force acting, because I have a current flowing through a length of wire in a magnetic field. So if you didn't get to here, you can pause and let's stop for the second half of the problem to calculate the forces. Now we know the magnetic fields at these locations. Let's determine the force. Well, the first force which acts on a wire, so if a wire of length, and I didn't specify before about, well, so let's say the length of these wires are L, which is in these, and then they go away from each other. So that's the length where they are. So the force acts on a wire of a length L, which has the wire has a current flowing through it, and this wire has to be in a magnetic field. This force acting on that wire then, which is part in a wire in the magnetic field, which has this current level, is given by this equation. It's proportional to the length, the current which is flowing through that wire itself, and the magnetic field at the location of the wire. And the direction of F is found using the cross product right-hand rule, because we have the cross product of the directionality of the current and the directionality of the magnetic field. So we know the current and the magnetic field have to be perpendicular to each other to get any force which is generated in a plane which is perpendicular to both those. And then this cross product means the magnitudes times the sine of the included angle on the plane, the smallest included angle between them. And this is the current in that wire. And this is the force acting on that wire. So we just think about wire 2 for right now. We've already determined that there is a magnetic field in that location generated by wire number 1, and this is the magnitude of that magnetic field. So we know the magnetic field, we know the current that's flowing through it, we know the length of the wire, so we know everything to determine what that force in that wire is. So determining the magnitude, we can do that. So length of the wire, this is the current now that's acting in that wire. Okay, so that's going to be my I2. So that's the current in that wire, and then so that's the magnitude of that current. The magnitude of the magnetic field at that location. So the location 2, we've already determined that's permeability of free space over 2 pi times the current from the other wire over D. So let's put that in there, and then this is the sine of theta. So let's think about, so we know the magnitude, let's think about the directionality now. So top view, first thing we worry about is the first term in this cross product, which is the current. So the current's flowing down from the side view, so in the top view, the current's flowing into the board. So that's my first direction. My index finger is pointing in that direction. That's my current direction. Then my middle finger is the direction of this magnetic field. Well, so I got to line this down, and then I spin around till this is pointing in the direction from the top view. The magnetic field's into the board, so that's the direction of the magnetic field. So you can see there's 90 degrees between those two, and those are both in this plane. And so the force is generated from my thumb. That's the directionality, and so that's going to be pointing to the right. So we know that these two vectors, the vector I and the vector B at those locations, are perpendicular to each other. So the sine of theta, sine of 90 is 1, and so this goes away, and I know my force directionality. The other way you can do it is the first term, put your fingers in that, turn your palm towards the direction of the magnetic field, so that's fingers into the board or down, and then curl my fingers in that direction there, stick my thumb out, forces out. I could do it from this view too. First part, current, the first term in the cross product, magnetic field, palm towards there, magnetic field goes into the board, force goes out. So everything's saying the force is acting to push this wire away from this other wire, and this is its magnitude. It's dependent on permeability of free space, the length of the wire, which makes sense. The longer the wire, the longer these two wires are parallel, the more force would be on them. It's dependent on, if I rearrange those, it's dependent on both the wire which is generating the magnetic field, this one, the magnitude of that current there, and the magnitude of the current through itself, all divided over 2 pi times the distance. The farther the wires get apart, the less force would acting. And so now you can look at this, you can solve for the second, what's the forces acting on the first wire. Solving now for the force acting on wire 1, we can say it's going to be very similar, except we're going to use the same formula. The length is going to be the same. This time the current flowing through that wire, current through number 1 is I1. That's the current flowing through that. And then the magnetic field at location I1 caused by wire I2 is this term. So you can kind of see that the currents have flipped around because it's depending, but I mean there's still a product, but this is the current flowing through wire 1, this is the magnetic field caused by the current flowing in wire 2. And so they have the distance between them and the length of the wire. And so we get the same magnitude as we did previously, because once again the theta is 90 degrees. So let's do the right hand rule to verify what the force direction is. So first we need to take the current flowing through that wire, and that's flowing, so that's flowing in the upward direction. Okay, so I put all my fingers in that direction. Okay, then the magnetic field caused at a location by this wire is into the board. So I put my palm there so I can rotate my fingers, stick my thumb out. So that says the force is acting in this direction. If I look from the top view, I can do the same thing. Stick my fingers in the direction of the board in, because that's the way the current's out. The current is flowing out from the top view. Current's flowing out. Okay, the magnetic field is in, so it's this way, and the force is there. So again, the same force. Or I can use my rule. First term in the cross product is I. So use this finger, point that direction of I, which is out of the board. This vector points in the direction of the magnetic field, your middle finger, and the force is out. So you can see these two wires are repelling each other. As you can try it out, or you can guess probably if you have both the wires having current flowing the same direction, what changes is then this magnetic field would instead of being so this one would still generate the magnetic field here in that direction, but now the magnetic field would be in the board, but the current level would be up. So if I did the right hand rule, I'd have current, magnetic field, and you can see that the force vector would be attracting this wire to that wire. The same thing would be true for here. I'd have this one would now have current going up here, which would generate a magnetic field so going up would make it generate a magnetic field here, which would be going out of the board. So current, the first term, times magnetic field going out of the board on this one would give a force in. So if the currents are going the same direction, they're both going in, going up, or both going down, they would be attracting each other and these wires would approach. If they go in opposite direction, then the forces repel. If one's going up and one's going into the board, then you'd have no force of attraction there. So that's a solving for this problem. If you understand this, you understand both how magnetic fields are generated by currents flowing on wires, and then how forces acting on wires which have current flow through them and also acting in the magnetic field operate. And if you look at the answer, it makes sense. Depends, the longer the length, the more the force, the higher either one of the currents, the more the force, and the farther apart, the less the force. And it depends on the permeability of free space.